A theory of everything, often abbreviated as TOE, is a single, all-encompassing framework that explains and links all physical aspects of the universe. This theory aims to unify the four fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Achieving a TOE would mean understanding how everything in the universe works based on one set of principles. It would revolutionize our understanding of the universe. Such a theory would not only explain the mechanics of the cosmos, but also answer profound questions about the nature of reality itself. It would bridge the gap between the very large, like galaxies, and the very small, like subatomic particles. Currently, our best explanations come from two separate frameworks: general relativity and quantum mechanics. These frameworks work well on their own but clash when combined. Finding a TOE would mean solving this clash and offering a complete picture of the universe. It could lead to new technologies and advancements in fields like energy, medicine, and materials science. General relativity is a theory developed by Albert Einstein. It describes how gravity works. According to this theory, gravity is not just a force, but a curvature in space and time caused by mass and energy. Imagine space as a stretchy fabric. When a heavy object, like the sun, sits on it, it creates a dent. Planets move around the sun because they follow the curves in this fabric. Quantum mechanics, on the other hand, deals with the very small. It explains the behavior of particles, like electrons and photons. Unlike general relativity, quantum mechanics is based on probabilities. You can't predict exactly where a particle will be, only the chances of it being in a certain place. This theory also introduces the idea that particles can be in multiple states at once, a concept called superposition. General relativity works well for large objects like stars and galaxies. Quantum mechanics excels at explaining the tiny world of atoms and subatomic particles. However, they do not fit together neatly. This is where the quest for a theory of everything comes in. Combining general relativity and quantum mechanics has proven to be a massive challenge. One of the biggest problems arises in extreme conditions, like those found in black holes. Black holes are regions in space where gravity is so strong that not even light can escape. They are formed when massive stars collapse under their own gravity. In a black hole, you have extremely high gravity, which means general relativity should apply. But you also have very small scales where quantum mechanics should take over. When scientists try to use both theories together in these conditions, the mathematics falls apart, resulting in nonsensical answers like infinities. Another problem area is the Big Bang, the event that created the universe. At the very beginning of the universe, everything was extremely dense and hot. Both quantum mechanics and general relativity should be at play. However, just like with black holes, the equations we use break down. To fully understand black holes or the Big Bang, we need a new theory that combines the principles of general relativity and quantum mechanics. This unification is the goal of the theory of everything. String theory is one of the most popular candidates for a theory of everything. Instead of thinking of particles as tiny points, string theory imagines them as tiny, vibrating strings. These strings can vibrate in different ways, and each vibration corresponds to a different particle. For example, one vibration might represent an electron, while another represents a quark. In string theory, these strings are incredibly small, much smaller than anything we can currently observe. The theory also suggests that our universe has more than the three spatial dimensions we are familiar with. In fact, string theory requires up to 10 or even 11 dimensions. These extra dimensions are thought to be curled up so small that we don't notice them in our everyday lives. The idea of strings and extra dimensions helps to unify the forces of nature. In this framework, gravity and the other forces can be described as different types of string vibrations. Despite its complexity, string theory remains a powerful and intriguing approach to finding a theory of everything. Section 5. Loop quantum gravity. Let's dive into this fascinating theory and how it quantizes space. Loop quantum gravity, or LQG, is another approach to unifying physics. Unlike string theory, LQG does not rely on extra dimensions or tiny strings. Instead, it focuses on quantizing space itself. In LQG, space is not continuous, but made up of tiny, discrete units called loops. These loops are incredibly small, much smaller than atoms. They form a kind of network which makes up the fabric of space. Just as matter is made of atoms, space in LQG is made of these loops. This network of loops can change and interact, creating the dynamic geometry of space. LQG also offers a way to describe gravity at the quantum level. By quantizing space, it provides a framework where general relativity and quantum mechanics can coexist. This means it could potentially solve the problems we encounter in black holes and the early universe. Despite its challenges, LQG remains a promising direction in the quest for a theory of everything. Section 6. M-theory. Explain its concept of branes and dimensionality. M-theory is an extension of string theory. It adds even more dimensions to the mix, suggesting that our universe might have up to 11 dimensions. In M-theory, not only do we have strings, but we also have higher dimensional objects called branes. These branes can be thought of as membranes that exist in various dimensions. There are different types of branes, such as one-dimensional strings and two-dimensional surfaces. These branes can move and interact in the higher dimensional space. Our universe might be a three-dimensional brane floating in a higher dimensional space. This idea helps to explain some of the strange properties of gravity and other forces. M-theory aims to unify the different versions of string theory. Each version of string theory can be seen as a different aspect of M-theory. Despite its complexity, M-theory provides a compelling vision of how a theory of everything might look. Section 7. Quantum gravity. Mention other emerging ideas in simple terms. Besides string theory, loop quantum gravity, and M-theory, there are other emerging ideas in the quest for a theory of everything. One such idea is the concept of quantum gravity. This term refers to various approaches that seek to merge general relativity and quantum mechanics. One example is the asymptotic safety approach. It suggests that gravity becomes simpler at very high energies, making it possible to combine it with quantum mechanics. Another idea is the causal dynamical triangulations, CDT. This approach models space and time as a series of small connected triangles that evolve according to quantum rules. There is also the idea of entropic gravity. These emerging ideas show the diversity of thought in modern physics. Section 8. Importance. Explain why finding a theory of everything matters for science and humanity. Finding a theory of everything is important for many reasons. First, it would give us a complete understanding of the universe. We would know how all the fundamental forces and particles work together. This knowledge would deepen our comprehension of the cosmos and our place in it. A theory of everything would also have practical benefits. It could lead to new technologies. For example, understanding the fundamental forces could help us develop new energy sources or advanced materials. These advancements could improve our quality of life and address global challenges. Moreover, a theory of everything would unify different branches of physics. Achieving this goal would be a monumental achievement for science and humanity. Section 9. Future. Mention current efforts and why this quest is significant. The quest for a theory of everything continues to be a major focus in physics. Scientists around the world are working on different approaches, from string theory and loop quantum gravity to newer ideas like quantum gravity. They conduct experiments, develop new theories, and use advanced technologies in their search. One area of current effort is in particle physics. Experiments at facilities like the Large Hadron Collider aim to discover new particles that could provide clues about a unified theory. Another area is in cosmology, where observations of the universe's structure and behavior help test different theories. The significance of this quest lies in its potential to revolutionize our understanding of the universe. A theory of everything would answer fundamental questions about the nature of reality. While the journey to a theory of everything is challenging, it's also exciting.